Okay, hi everyone. Here's the second type of chemical equilibrium problem that you'll encounter. It's called an extensive dissociation problem. And it's similar in many ways to the previous example. Right? You're given some component, you're given some information about it at equilibrium, and then asked to calculate Ks and delta Gs and such. The problem here is that this dissociation is given as a percentage. And so the idea here is that when you are solving dissociation problems, you have a pure component, in this case water, which is dissociating into its component species. Right? And I guess I'll just hop right into it. The first step when you solve these types of problems would be to write the relevant reaction and set up an ICE table. This one is a little bit more involved because we're not given the reaction straight away, but we can figure it out. So here's the reaction. I'm going to take H2O gas, water, which is going to dissociate into its component species. One thing I want to emphasize to you is that when you write these reactions, when you write reactions for extensive dissociation problems, you should write this for 1 mole of reactant. Right? And I can tell you why later, but ultimately that will be helpful. So the dissociation reaction for 1 mole of H2O is written here. The second thing to do is set up an ice baby table. So again, it's going to look like this: H2O, H2, O2, ICE. All right. What you may be wondering here is, well, what goes in these columns? Right? You're not given any amounts in the reaction. What you are given, though, is percentages. And so when you have these extensive dissociation problems, you think of them as percentages. If I have a pure reactant, right, that's 1. It's 100%. It's pure. And I have no hydrogen or oxygen. Right? This is what I mean by a dissociation reaction. Pure H2O dissociating into these species. Based on the stoichiometry, you can figure out the change. And I don't exactly know why, but in extensive dissociation problems, we typically write the dissociation as alpha, not X. So this is a reactant. It's minus alpha. This is plus alpha. This is plus 1/2 alpha. Once I have that, I can figure these out. 1/2 alpha. Okay, step 1. Step 2, write an expression for KEQ. And away we go. KEQ equals, and I'll write the reaction again up here just so I have it. H2 plus 1/2 O2. It's equal to the partial pressure of H2O over P standard times the partial pressure of O2 P standard raised to the 1/2 divided by partial pressure of H2O P standard. Again, these are written in terms of the partial pressures of the species. I don't have that. What I want to do is express these in terms of the mole fraction. These. So just like last time, whoops, Pi equals Xi P top. So in terms of the mole fractions, this is XH2 P tot P standard, XO2 P tot P standard raised to the 1/2, XH2O P tot P standard. Simplify, this will cancel, and I'm left with an expression that looks like this: XH2 XO2 raised to the 1/2 over XH2O times P tot over P standard all to the 1/2. That's my expression for KEQ. Whoops, last but not least, I have solve as appropriate. I'll write that in there. That was my third step. I don't know how it didn't make it, but it didn't. Appropriate, I think that's right. So we just had an expression for mole fractions. I want to convert all of these equilibrium amounts then into mole fractions. If I add up the total amount of material that's present, I'm going to get 1 plus 1/2 alpha. I can then calculate the mole fractions. 1 minus alpha over 1 plus 1 alpha minus alpha over 1 plus 1/2 alpha. I don't know why I wrote this as a minus. It's not a minus, it's a plus. Plus alpha. And then this is alpha over 2 times 1 plus 1/2 alpha. For reasons which I hope become clear here in a second, I'm going to write this in a slightly different form. I don't like this 1/2 alpha here. So I can write this equivalently as 1 minus alpha over 2 plus alpha. Basically, I multiply the numerator and denominator by 2. This is 2 alpha over 2 plus alpha. And this is alpha over 2 plus alpha. Plug things in into my expression for KEQ equals 2 alpha over 2 plus alpha times alpha over 2 plus alpha raised to the 1/2 over 2 times 1 minus alpha over 2 plus alpha. P tot, P standard raised to the 1/2. Cancel, 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 cancel. Just my 2 cancel. Right? If I do all of this right at the end of the day, right, what I'm going to get is an alpha to the 1/2 over 1 minus alpha 2 plus alpha to the 1/2. Again, I'm just going to plug this in because it's going to go away in a second. Actually, I think this was 1 ATM. So it's actually 1.01 bar, all raised to the 1/2 power. Alpha times alpha. I lost my cursor somehow. Oh no, I lost my pen. Let me try. Oh, okay, forget that. There it's back. Alpha times alpha to the 1/2 is alpha to the 3/2. And now this becomes a plug and chug. What you were given at the very beginning was 1.77, right, dissociated. What that means is that alpha equals, 0.0177 in terms of a percentage. Right? At equilibrium, if I started with 100% H2O, it's now 98% H2O. So I can take that number and I plug it in. 0.0177 to the 3/2 divided by 1 minus 0.0177 times 2 plus 0.0177 to the 1/2. Again, I made a mistake before, so bear with me. 177 to the 1.5. If I'm doing all of this right, the number I get out at the end of the day is 1.69 times 10 to the minus 3. Right? That's my equilibrium constant. This should make sense. That's a small number. It's less than 1. Suggests that the reactants are strongly favored. And that's consistent with this notion that this is weakly dissociated. It's only 1.77% dissociated. So it all works. Again, you can go through and plug it into your formulas and calculate those other things. Hope all this helps, and I will see you next time for a discussion about changes in equilibrium to something other than the standard state.